Today I will show you the code inside this light controller board. Well, actually, this one. This is my first go at designing a fully finished product. Even though I'll only talk about the code in this video, I wanted to show you this because I'm really excited, and the next video will be about how I assembled it and talk about what sort of stuff ups I did and how to fix them. What's up everyone, my name is Sim and you're watching smartESThouse, a channel where I show you how I design and build my smart home. If you're new to this channel, want to see more of what I do and want to learn how to create DIY projects for your own smart home, start now by subscribing and make sure you click on the bell icon so you would get notified when I upload a new video. So, as I said, I'll only talk about the code in today's video in this microcontroller, but I wanted to give you a quick rundown of what this board is really about. So, as you can see, there's 6 outputs for mains, each having their own fuse. This is the mains input, and this is each individual output. This is the 12 volt AC input for zero crossing detection. These two headers are for 5 volt power and I2C communication. There's a header for serial communication and a header for burning the bootloader on the chip. I'll be going through the code and explaining it line by line, and if it's something you feel like you don't want to see, I also have a quick demonstration of the board in action at the end of the video. So skip over there if you want to see that. But I think the code is pretty interesting as well. So without further ado, let's go. First off, I have to include Arduino.h because I'm using Platform IO rather than Arduino IDE. I definitely recommend using Platform IO instead of Arduino IDE because it's just so much better. Next included is wire.h, and this is the I2C library. After that, there's 2 integers, t1 load and t1 comp. t1 load is used to reset timer 1, and t1 comp is timer 1 compare value. I'll talk about it later. After that is the I2C address, and this needs to be different for every slave board when joining the I2C bus. Then there's cycle count. If you remember from the last video, I talked about how I divided each AC half wave into 100 equal bits, and this just keeps track of which part of the half wave we're in. After that, there's an array called requested state, and this array is where all the states for the pins are stored. Each element in the array corresponds to a specific output. So element 1 is output 1, element 2 is output 2, and so forth. Now we're going to move into void setup. Here I set up serial, and this is mainly just for debugging. Next I'll join the I2C bus with the I2C address and set up on receive event I2C receive, and you can see the function up here, and I'll talk about it later. After that, we're going to set up timer 1. This register sets the prescaler for the clock. This one resets timer 1, and this one sets the compare value. Once that's done, we're going to set up external interrupt. This line sets the int0 pin as output. And I use direct port writes because it's just so much faster. When time isn't critical, I do use digital write as well, but at the moment I want to be as fast as possible. Next line defines when the interrupt is going to be triggered. And by setting this register to this bit, we select any logical change on int1 pin to generate an interrupt. So that means either if it goes from 0 to 5 volts or 5 volts to 0 volts, it's going to trigger one. And after that, we're going to enable the external interrupt by setting the int0 bit in this register as 1. And last thing in the void setup is a simple for loop where I set all the triac pins as outputs. And because I've chosen all the outputs in port B, it's just one line of code. After void setup is done, the program automatically goes to void loop, but as you can see, it's empty and it doesn't have anything to do here. All we do now is just wait for the int0 interrupt service routine to trigger. Once it does and zero crossing is detected, first thing we do here is enable timer 1. And then we move away from the ISR as quickly as possible. And this is just a good habit to get into because interrupt service routines cannot be interrupted by another interrupt. So we move from interrupt service routine to zero crossing ISR, and this is just a function I made, and this is up here. In this function we have a for loop that counts from 1 to 6. Within each iteration we check if the ith element in requested state array equals cycle count. So at first cycle count equals 100. Because we just started the for loop, I is 1 and the first element in requested state is 0. That means 0 doesn't equal 100 and we don't go into the if statement. But let's say it does. Requested state for output 1 is 100. We go into the if statement and here we just write the corresponding bit in port B register to 1, thus writing the output high and turning the triac on. Once we've done this 6 times, we go here and subtract 1 from cycle count. Cycle count was 100, now it's 99. And we just wait for the next interrupt. The next interrupt to trigger is timer 1. And in the timer 1 ISR, we move away from the ISR as quickly as possible, as with the zero crossing interrupt. And go into timer 1 ISR function, another function I made. In here, the first thing we do is reset timer 1 because we want to get an accurate count. Next, we check if cycle count is larger or equal to 15. I chose 15 because when testing different lamps, I noticed that if the lamp is turned on under 15% of intensity, it either flickers, doesn't really turn on. All in all, it was pretty useless. So I thought this would be a good cutoff point, so we wouldn't have to do unnecessary work. If cycle count though is larger or equal to 15, we go into the if statement. And here's another for loop, and this is identical to the one in zero crossing ISR. We check if the ith element in requested state equals cycle count, and if it does, we write the pin high. But let's say we've done this over and over again and cycle count is 14. We don't go to the if statement, but rather the else statement. Here another for loop, but instead of comparing ith element in requested state to cycle count, we compare it to 100. And if it doesn't equal 100, that means the pin doesn't have to be fully turned on, we write the pin low. We have to do this because if we don't turn off the triac gate, it will stay latched and will stay on for another AC halfway. Once we've turned off all the pins we need, we make cycle count 100 again, ready for the next cycle, and disable timer 1 because we don't want to get any unnecessary interrupts. And that is pretty much the whole cycle for dimming 6 outputs. Now to receive commands, we have set up I2C. When communication is detected, we go into this function. Here's a while loop that loops through while we have any bytes to read. And because I know I'm only going to send 2 bytes, pin number and pin state, I first read I as pin number and J as pin state, and then write J into the ith element of requested state array. And that is it, it's that simple. I still need to add a bit of code so that the slave would send status updates to the master. Plus I want to make something so that the state doesn't change instantaneously, but rather have a bit of an animation to it. But that's all gravy. And this is the code in action. The lamp you see here is lit at 50%. Notice that you can't see any flickering or any inconsistencies. The code really works well and I'm really happy with it. My camera shutter speed is at 1/24th of a second. Now look at the same lamp at the same intensity with the shutter speed at 1/96th of a second. And now at 1/1536th of a second. Now you can see that the power is actually turned on and off, but it's way too fast for a human eye to detect, and all we see is just a nice dimming effect. And that is it for this video. I won't publish the code just yet because, as I said, there's still a few things I want to do to it. But as soon as I do, I'll let you guys know and make it available. If you like this video, give it a thumbs up, share it with your friends, and also don't forget to subscribe. In the next video, I'll show you how I assembled the board, talk about what sort of stuff ups I made when designing it, what sort of troubles I faced when programming it, and also a couple of good things I found out that are actually going to make my life easier. But until then, take care and I'll see you next time.